I'm now going to use the binary heap as a priority queue to solve another problem that might arise. In graphs that are undirected, one often wants to know what is the minimum spanning tree of that graph. This is the definition of a subset of the edges, that if you remove all the other edges, you still have a connected graph, which means you can get from any vertex to any other vertex. But you've reduced the total accumulated weight of all of those edges. And this is a structure that can be used to solve a numerous number of problems. I'm just going to show you an algorithm that computes the minimum spanning tree. It's called Prim's algorithm. And it starts with an undirected graph who's got vertices and edges. And I'm trying to compute which subset of edges will form what would otherwise be known as the minimum spanning tree. In this example here, you might look at these edges, and I'm highlighted 4 of them in particular. If I add the edge weights of all of those, the 2, the 3, the 1, and the 5, I'll get to 11. And it turns out that while you may find other subsets that equal that same total, you can't find another subset of edges which has a smaller aggregate total and still retains the connected property of the graph. I'm going to demonstrate now in Python how to compute the minimum spanning tree for an undirected graph using the binary heap data structure. The way Prim's algorithm works is by processing the graph one edge at a time, and in greedy fashion, just like you saw for Dijkstra's algorithm, it only adds edges whose a total accumulated weight continues to maintain the property of being the minimum that it's seen so far. I'll first start with a general description of a graph, the one that I just showed you on the slides. This is an undirected graph, and once again, I'm using a dictionary to store it. Each vertex has a list of edges. Each edge has an edge weight associated with it. Now, Prim's algorithm has to maintain one extra challenge, and its challenge is, at certain times in the algorithm, it needs to know whether the priority queue contains a certain vertex. I've already mentioned this basic problem with priority queues, is that in the general data structure that's given to you, you can't just go searching through the priority queue to see if it contains something, because that's an order n operation. And you're usually doing that step in a larger loop, which is itself an order n operation. And we want to avoid the order n squared behavior and try to come up with an algorithm which is order n log n. So to solve this one problem, I'm going to use some additional storage to keep track of whether I know that a particular vertex is in the priority queue. This is another example of a time-space trade-off, where I may use some extra storage, and as long as it's reasonable and order n extra storage is reasonable, then I'll still be able to produce the efficient algorithm that I desire. We're going to start here with my graph, and once again, go through and find each vertex and assign it a positive number. I'm going to use the word key here. It's the equivalent of the disk that you've seen for Dijkstra's algorithm. Initially, they're all infinite, and I have no predecessor link information, so I set it to none. I'm going to go through and create a binary heap where each vertex that gets put in there is in fact going to be stored with a priority equal to that key value, which right now is infinite. And I only have that initial one that I pick at random to start. I'm going to go through and pick a vertex from the priority queue, the one that is closest, the one that has the lowest nominal cost, which means the highest priority. Once I've removed it from the priority queue, I remember that it's not there, and that's my in-queue array that I just update to be false. Once I picked out that vertex from the priority queue, I now need to look at the neighbors of that vertex. For each of those neighbors, I check, is it in the priority queue? That means it's still at play. And I find the edge weight that I have from the vertex I've just removed from the priority queue and all of its neighbors. If it turns out that that edge weight is smaller than my current key value that I'm associating with the vertex, then I'm going to change its priority in the priority queue and record that weight. You see the structure is identical to Dijkstra's single source shortest path algorithm. I have a loop where I'm pulling elements out of a priority queue. I've set it up in advance to start with some initial values that are infinite. And as the iteration processes, I manipulate those values, making them smaller and smaller to reflect the actual structure of the minimum source tree that I'm trying to compute. And then, once it's done, I have a solution function that goes through and recreates a solution. So while I don't have time to do a full treatment on the minimum spanning tree problem, I can at least show you that it works. So if I have my graph, which we've seen, and I compute the minimum spanning tree of that graph, it's going to give me these edges. And what I'm going to do is put these edges together to at least show what they are. So I compute my minimum spanning tree of the graph, which is an efficient operation using the n log n behavior of MST. And I look for a solution of those, and it comes out and tells me these are the edges that you want to have between 0 and 1, 1 and 2, 2 and 4, and 2 and 3. And if you go back to the slide definition that describes the minimum spanning tree, you see that these are indeed the edges of that solution. I wanted to show you this here to demonstrate a fundamental property of the binary heap. It's a versatile data structure, and it's used in a number of algorithms. And all I've shown here is how you just dropped it on in and used it to solve the problem at hand. As long as it implements the decreased key operation that is needed for this algorithm, then you can make it work. But you can't just take a priority queue implementation off the shelf, because they don't have that implementation in their API. You need to develop a binary heap whose structure is based on the heap that I've already introduced. And with that, it produces a versatile data structure that you can use to solve a number of interesting algorithms. This completes the description of the minimum spanning tree problem.